Hi, I'm Dr. Nick Gowland, Business Development Manager at the Graphene Engineering Innovation Centre, and you're watching our Challenges and Opportunities in Graphene webinar series from the University of Manchester. In this episode, we'll hear from Dr. Lisa Scullion, who is our Application Manager for Coatings and Membranes, and she'll be talking about how graphene could transform the durability and anti-corrosion properties of protective coatings and paints in industries such as aerospace, automotive, marine, construction, and many more. Welcome everyone, thanks for joining the first GEIC public webinar. Really great to have so many people here. We've got people from India right their way through to the US and Sweden and Argentina and Brazil, so really happy with that. Thanks for joining. Very quick intro to Lisa Scullion, Dr. Lisa Scullion, apologies. So she is one of the application managers at the Graphene Engineering Innovation Centre. She manages the Membranes and Coatings Lab. You have a team of about 4 or 5, is it? Specialists and technicians, Lisa? Yeah. So she'll tell you a bit more about the GEIC, as we call it, later on in her presentations, but she's going to talk to you today about challenges and opportunities in graphene coatings, as you're aware. So Lisa comes from just over a decade in industry, so 2 or 3 years were spent at Unilever as a formulation chemist. She's also worked 7 years in a polymer technology company. She's set up supply chains, she's worked in product management, a little bit of marketing, and she's been with us at the GEIC just over a year. She's also involved with the European project we're doing, the EIDF project, but mainly she's doing coatings, membrane projects with industry. So I'm going to hand over to you now, Lisa.
Thanks, Nick, for the introduction, and really thanks everyone who's taken the time to come and listen today and hear about graphene coatings. And I'm really quite thrilled that there's people really from all over the world here today. It's very exciting. As Nick said, I run the coatings team at the Graphene Engineering Innovation Centre, or the GEIC, and I've been here just over a year. My team and I have basically set up this coatings lab from scratch over the last 6 months to a year. We've got in a lot of coating equipment and testing equipment, chemical and mechanical, and I'm lucky that I have a team with lots of experience, both from industry and from academia. I know there's a lot of people here today from lots of different industries, so I really hope you'll find it informative. And if you haven't dealt with graphene before, it should be a good introduction to graphene as well. I also know that there's a lot of people from academia and from Manchester here who probably already know a lot about graphene, but it's probably a chance for you to see what kind of things we do at the GEIC and how we take things from base level research and take those next steps into developing real products and scale up. Okay, so this is the agenda for the things I'm going to talk about today. I'll start with a short introduction to graphene because we do need to start there, and the variety of different graphene related materials, which is a term you will hear a lot from here on in. As far as opportunities are concerned, I'll talk in a bit more detail about anti-corrosion applications, mechanical improvements, fire retardancy coatings, and then I'm going to go through some of the main challenges that we come across. Anyone who formulates with graphene will have come across these same challenges, and namely their dispersion and your choice of materials is very important. Just at the end, I'll go over some other applications briefly, and then I will tell you, as Nick said, a bit more about the GEIC and what we do and how we engage with industry. So firstly, as an introduction to graphene, I mean, I'm aware that lots of people already know about it. It's probably why you're coming to this talk today. We know that graphite's already a very impressive material. It's a good conductor of heat and electricity. It's chemical resistance. But graphite itself is basically made up of these planar layers of graphene, which are hexagonal, sp2, bonded carbon atoms, and the spacing between each of these layers is about 1/3 of a nanometer. When you isolate a single layer of graphene from graphite, it takes on whole new properties. It's got these remarkable properties that are very different from the bulk material, and it's got incredible strength and stiffness. Some groups have measured its tensile strength as 130 gigapascals with a modulus of a terapascal. That's huge for something that's essentially a two-dimensional material. It's got excellent conductive properties, thermal properties, and because it's just an atom thick, it's virtually transparent. So this is all groundbreaking data, and I mean, that's why we do this here in Manchester, and that's why the measurement and isolation was Nobel Prize worthy. The images on this slide just show the bonding arrangements of carbon atoms within the planar structure, and some images of some few layer graphene as well. So the box on the right here, can you see my mouse pointer, by the way? Is it moving? Okay.
Yeah, we can. Yeah.
This box on the right has got a list of the different forms of graphene-related materials. And for anyone new to graphene, I think this might be the take-home message today, that there's not one type of graphene. And I'll explain the difference now before we get into the main section on coating. So these images here, they show the 4 main forms of graphene that we use for R&D and on the industrial scale. So here on the left, obviously that's just a piece of graphite. It's got multi-layers of carbon atoms. It's very highly ordered. And you can see these layers easily using SEM, or scanning electron microscopy. Image B here is an SEM image of a single graphene sheet. And it's probably worth explaining quickly here about the 2 main methods of making graphene. To get a single perfect layer, you essentially have to grow that graphene using chemical deposition techniques from carbon-containing gases, or you have to go down the mechanical exfoliation route, as you would do with the sellotape method. And that's how you go about getting that 1 atom thick perfect graphene, like the one in the image. The section on the right is labeled as bulk applications. So these are far more industrial, scalable routes to making graphene, and we call that the top-down approach. So mechanical or chemical exfoliation essentially separates the layers of graphite out into graphene, and then we end up with graphene of a few layers. So that can be 1 to 100 layers thick. But these graphene nanoplatelets, as we call them, they still display a lot of the functionality that you get with single layer graphene, but they can be produced at scale, and they can be produced as a powder, so you can then use it as an additive like you would any other kind of additive powder. The next image along here shows graphene oxide, and this is the most common functionalized form of graphene, and you'll hear about it a lot. Some of the carbon atoms here are functionalized with oxygen containing groups, so carboxyls, hydroxyls, epoxy groups. And there's quite a few reasons why you'd want to use graphene oxide over graphene. Firstly, it's quite straightforward to make. It's an easy chemical route, and what you get when you produce graphene oxide is a stable aqueous dispersion, and that's because obviously with all the groups on it, graphene oxide is far more hydrophilic than graphene. It's then very useful to have that in dispersion form to dose into other systems. Although with that functionalization, it does come at the expense of some other properties, say electrical properties of the graphene. Also, because it's got these functional groups, it's got more bonding sites. So sometimes you want to use GO instead of graphene because it's more compatible with organic systems, so polymer systems, for example. Finally, on the right, we've got reduced graphene oxide. And as the name suggests, that's graphene oxide where we've taken away those groups, those functional groups, and we've reduced it back down. And there's lots of reasons why we would take that route to get graphene-based materials. Very often it's easier to use graphene oxide and then reduce it than to try and do the same thing using graphene straight away. But I won't go into too much detail about that just now. So we come to the main question really is what are the benefits to using graphene in coatings? And I'm going to go over some of these benefits broadly, and then I'll look at some of the applications and the science behind them in a bit more detail later on. Just to be clear here, what we're talking about is traditional coatings, protective coatings, paints, the use of graphene to form nano-composite coatings, not single layer graphene coatings or very, very thin graphene films, the kind that you get with more sophisticated chemical vapor deposition techniques. There is actually an upcoming webinar next week which deals with that, those sort of systems. So I'd certainly recommend going to that if you're interested. So I won't be covering that kind of coating today, just the kind of polymer-based nanocomposite coatings. So the graphene that we'd use in those kind of coatings is very much kind of top-down, mechanically or chemically exfoliated graphene. So firstly, we can look at the strength properties of graphene. All these properties have an effect on a coating system. So if you have graphene incorporated into a nanocomposite coating system, it can show enhanced toughness. It's stronger. It can help issues such as abrasion and wear and scratch damage. Because the surface of the coating is tougher, it's better resistance to impact. And this is relevant to coatings over lots of different industries. Anything that's subjected to extreme external forces or moving parts. There's also quite a bit of research that shows that graphene can offer UV protection from UV degradation as well. There's quite a bit of work in this area. Again, that can kind of span over lots of different industries, not just coatings. The second big feature of graphene, as you probably know, is that it's a barrier. It's got extreme barrier properties, and it can help things like corrosion. So coatings that are exposed to elements or extreme conditions. There's a lot of interest in this area from marine applications for that reason, especially as graphene-based coatings are starting to become commercial now. So there's a lot of interest from a lot of different areas. Anywhere where you need general metal protection or paints. And it's not just traditional corrosion either. So we're talking things like packaging, food packaging, protection from acidic or aggressive ingredients. Also, graphene's got a huge surface area, and we can control the surface area and tune the surface chemistry. So if you think about it, different pollutants have affinity for different surface chemistries and morphology. Graphene has all these absorption sites, which means it's being studied for the absorption of pollutants within coatings, heavy metals, gas, waterborne pollutants, all kind of things. And lastly, there's a lot of interest in using graphene in polymeric fire retardant coatings. So here it acts as a physical barrier, and it helps in lots of different ways to prevent surface damage. And it can also be tuned to interact with the polymer to change its thermal properties. For example, the melt viscosity in positive ways. But I'm going to talk about that in a bit more detail later on. So how does graphene help corrosion? There is a lot of literature. There's an awful lot of research in this area. There really is. And there's a lot of good results coming out from lots of different research institutions. One of the reasons to look for alternative materials is because there's so many restrictions now, certainly in the metal protection coating industry, around certain transition metal use. Chromium is the obvious one because of its toxicity issues. So these additives, the constituents, they're very restricted now, and you have to use them at very low levels. Graphene's attractive in that sense because it is just carbon, so it's a potential environmentally friendly substitute for other hazardous materials. The reason it helps with anti-corrosion, again, is down to its structure. So if you look at the diagram again of graphene, the bonding arrangements of the atoms are important, and also its incredible chemical stability. The hexagonal arrangement has pores in between the hexagons, and these are tiny. These are less than 3 nanometers. And the way that the orbitals are arranged in this bonding configuration means that graphene has a delocalized electron cloud on it due to these double bonds, this pi conjugation, and this provides a repellent field almost and helps to block these pores even further. If you think about a single layer of graphene on a metal surface, can completely block diffusion of gases such as oxygen to the metal underneath. And obviously we're not using that sort of graphene in coatings here. We're using more industrial scale, but the principle is still the same. So that big surface area and its 2D nature of graphene, it makes physical barriers within a coating structure. So the mechanism for anti-corrosion with graphene, it's fairly well understood. If you look at the diagram here, essentially graphene in the coating extends the path length of corrosive media or the electrolyte down through the coating to the metal underneath. And through the coating, the graphene, the way the graphene layers are positioned, stop those ions or those molecules having a direct route through to the surface. And we tend to refer to that as the tortuous path analogy, which you may have come across many times. Also, when you apply a coating, when you process it, when you use an application procedure, when you cure it, you can get defects within a coating. Obviously, you can get micropores, nanopores, and it's suggested that because of the surface area of the graphene and that layered structure, you can actually block the pores of the defects in the coating as well, and that also helps to block routes down to the metal below, which would be there in a normal coating. Obviously, corrosion takes place over a long time. So if we're going to look at anti-corrosion coatings, we have to do long-term testings. One of the ways we do that is to do corrosion testing in a salt spray chamber, and we can also do electrochemical measurements such as EIS, and I'll show you a few examples of that just now. So lots of groups have shown how graphene affects coatings quantitatively through electrochemical measurements. And EIS is electrochemical impedance spectroscopy, and it's a technique that essentially measures the ability of a coating to impede the flow of current, and it's directly related to corrosion. And the easiest way to compare the effects with different coatings is to compare different values for the impedance modulus. There's a few examples from the literature I've just put in here. So these graphs on the left of the slide, they show a Bode plot, which is impedance versus frequency for a polyurethane coating that's been exposed to sodium chloride solution over time. And then next to it is another plot for the same coating, but that's been modified with 0.2 whip% of graphene oxide. And what you can see is the polyurethane coating with no graphene. It shows fairly good initial impedance up to about 10 to the 8, but then it drops dramatically even after just 8 hours of exposure to electrolyte, and it ends up dropping down to about 10 to the 6. After 100 hours, you can see that corrosion is occurring. If you look at the graph to the right, though, the one that contains 0.2 whip% of graphene oxide, the impedance starts high and it pretty much stays there. Even after 236 hours of testing, it hardly drops at all, and it shows you that huge difference that a very small amount of graphene can have on a coating. The picture insert there is a TEM image of the geodisperser of the coating, just so you can see it up close. The other graph on the right, again, we're looking at impedance modulus in a Bode plot, measured for an epoxy graphene composite coating with different loadings of graphene. And this is just graphene nanoplatelets. It's not geo, and it's been loaded with 0.1 to 3% by weight of GMP. The coatings have been subjected to salt spray testing for 200 hours before they've been measured. And what you see here is for the neat epoxy coating down here, the values are very low. It doesn't do well in the test at all after 200 hours. But if you go up and you look at these high lines, about 0.5, 1% weight inclusion of graphene shows a really high impedance modulus value. Even after salt spray testing, it's up about 10 to the 9. And that's really very good compared with the neat epoxy.
Lisa, quick question from Steve Hodge at Bessarian.
Yeah.
Are these coatings with other fillers, for example, zinc?
Sorry?
Are these coatings with other fillers as well, for example, zinc?
I don't think these are from memory. I'd have to check the papers again. But yeah, I am talking about additional fillers later on.
Okay, cheers.
Yeah, I know what you mean. If they got extra sacrificial fillers in there, I don't think they do from memory when reading the papers, because I think that's why I picked them, because they were direct effects of graphene.
Okay, thanks.
This graph's really useful. I think it gives so much more information than pass or fail. Does graphene work well? Does it not? It gives information on dose and critical limits. If you look at the low dose levels, the kind of 0.1%, the blue line here of graphene, the result's not as good. And that's probably because the addition level is actually too low to form that barrier network in the coating. And likewise, although slightly better than the neat epoxy, the 1%, the 3%, sorry, the 1.5% and the 3%, they gave lower performance as well, and they lose efficacy. And this is probably due to dispersion and agglomeration issues, which I'm going to discuss in a lot more detail later on. So for that reason, it's a good graph. There's lots of reasons why people would want improved mechanical properties for coating, better efficiency, performance, increase of working lifetime, aesthetics. People don't want scratched and messed up coatings. And as I've said a few times, graphene can effectively toughen and strengthen a surface. It's got really high tensile strength and modulus, and this strength is down to these strong bonds and the way it's covalently bonded together. When it's subjected to mechanical force, graphene can also transfer stress very effectively because of its structure through a matrix material, and it can help to stop crack propagation or even bridge cracks. And again, that's down to its unique structure. This picture on the right is quite nice just because it's a close-up image of the graphene bridging cracks, and this is within a ceramic surface. I just think it's quite a powerful image. If you have a coating with poor abrasion properties, it means that you lose some of your material from the surface. It's easy to rub off, it's easy to scrape off, and that's very important for coatings that are subjected to stresses such as bearings or wire for joints, that kind of thing. And graphene toughens that surface because of that high tensile strength and the bridging network, and resists that permanent deformation, let's say. There's some literature around that says graphene can suppress wear up to about 30 times more than graphite-based additives in similar coating systems. So there's a lot of work going on in this area. The next application I'll talk about is fire retardant coatings. Carbon materials are already used in fire retardant coatings, graphite, carbon nanotubes, but people are obviously looking into graphene now to see whether that can improve on the properties. One of the benefits of using graphene is loading levels. If you're using traditional inorganic fillers within a fire retardant polymeric coating, you have to use lots of it, very high dose levels, and you can potentially use graphene instead and use much lower levels. High organic fillers can tend to lead to aggregation and dosing issues. Also, you can use it in conjunction with other materials. So you might get a synergistic effect where you end up using less of both materials to get a bigger benefit. Graphene's non-toxic. You're not going to get those toxic byproducts that you would from other flame retardant constituents. The way it works, one of the ways it works to help with these coatings is it forms a beneficial char. It's got a unique aspect ratio and it's got a layered nature, and you get this char that's formed is dense and it's continuous. And it's another example of graphene being a barrier. This is a physical barrier that prevents the transfer of heat through down to the surface underneath, or it prevents transfer of unwanted combustion products through the coating back out into the atmosphere. And it's back to this tortuous path phenomenon again. It's a barrier effect. And the graphene materials, graphene's very thermally stable. and this carbon scaffold, it acts as a template for this char formation. Graphene can also improve the thermal stability of polymers by forming networks. It can affect TG, melt viscosity, prevent dripping, delay ignition temperatures. There's a huge amount of work in that area as well, and especially if you're looking at graphene and graphene oxide based flame retardant materials. The image on the right here I've just included because it's quite compelling. It shows if you use reduced graphene oxide and then reduced graphene oxide in conjunction with another material. It's actually sodium metaborate, and you can see that over time, as you put a flame to the material, you keep the material intact. Basically, this one goes up to 2 minutes, and you've got no effect pretty much on your graphene. So this is just dip coated paper. All the references for these are at the end, so anything you want to read in detail, you can go through them afterwards. So I've talked quite a bit about the challenges, the applications and the benefits, but I need to talk a little bit about the challenges. And one of the main ones, which has sort of already come up, is about dispersion. So it's a key part of the process. It's one of the things that everyone who formulates with graphene has to deal with. Graphene doesn't disperse in the same way that other fillers do, traditional pigments or anything like that, because of its structure and its aspect ratio. It's not plug and play. You can't just put graphene in the same way that you do with other things. Graphite's happy being graphite. We go to all this trouble to make these 2D materials, but then we mix it with something, and the tendency is for the graphite to want to restack. It's got all this surface area and these van der Waals forces. It wants to go back to being graphitic-like. So this is a problem because you can get large amounts of agglomeration when you mix graphene into different systems and different coatings. So you really have to start thinking about processing techniques. So milling, high shear, dispersion, maybe the use of rheology modifiers to keep that graphene dispersed while your coating is curing. There's so many things you have to think about. The other thing you can do is to functionalize the graphene, and that can help with dispersion, especially if you're in sort of an organic polymer matrix. Geo, for example, it's got all those oxygen groups and can help dispersion, and those functionalized groups can help prevent agglomeration as well. There's so many ways to modify graphene: silane, halogenation, nanoparticle grafting, grafting on poly. The topic's huge. You could do a whole webinar on it. So I won't go into too much detail. It might be something we'll do as a webinar later on. And here we're talking about choice of materials again. Here, this is what I referred to just before. It's how the lifetime of a coating is affected by different flake sizes. So this is lateral size. So this is work that was done at the University of Manchester to show how a coating exposed to salt solution to show its lifetime, basically. And there's a clear response based on the flake size. So here, there's an optimum flake size. It's about 15 microns, so it doesn't follow a trend. It's not the bigger the flake, the better, or the smaller the flake. It depends on the system, and it depends on the coating that you're putting it into. So that's something you have to bear in mind. And there's so many other things to think about with graphene, is where it comes from, what specifications, what's the variation in layer number, what's the variation in flake size, how is it made, is it chemical, is it mechanical, you know, the quality, the price. So many things to think about, and that's kind of because graphene's sort of still in its infancy compared to other materials. But I think it's fair to say that the graphene global community is making a huge effort in standardizing these materials, setting up supply chains, getting quality reproducible graphene sources. And there's already quite a few really good suppliers of graphene who do that at ton scale now. Testing wise, oh, sorry. You have to do all the same testing that you would with any other coating when you're using graphene. And one of the things you have to think about is whether the cost of adding in graphene is worth the performance increase that you might get. And some people cost it in straight away. They might think, oh, graphene's expensive. But you might get performance increase where you actually use half the amount of coating because the performance is so good. So you have to balance these things out. Dispersion here again is an issue. If you're going to make a coating that needs a certain shelf life, then you have to do some work on that dispersion. You don't want your graphene crashing out of solution when it's sat on a shelf for 6 months. And also you have to think about standard product development issues, the environment your coating is going to be in, maximum temperatures, whether it will go through any freeze-thaw cycles on transport. So that's all obvious things to anyone in the coating industry. Very quickly, other applications. There's so many applications for graphene that we do, certainly at the GEIC. We do composites, we do energy, we do printing. But I've picked out a few topics that are more relevant to coatings, let's say. One of them, the big one, is membranes. Membranes is big at Manchester, and a lot of the coating science is directly related. One of the things we're doing when we're making membranes is we're tuning the pore size of the flakes within a pure graphene coating to allow different molecules to go through, sort of a filtration system, so you could get oil and water separation or desalination. And we can control pore size down to tiny amounts, 1 or 2 nanometers. Packaging, I mentioned briefly at the start. Again, we can make something that's a complete barrier, or we can tune the coating so that certain materials can go through, and certain materials can be kept out. Textile coatings, we do an awful lot of as well. I haven't covered it a lot, but it lends itself to those same properties. So maybe fire resistance or moisture resistance, hydrophobicity, strength of fibers. Sensors, you get a huge amount of surface area, so you can get very sensitive architectures of graphene. The sensors and the textiles often go hand in hand if you're looking at that kind of wearable tech area. Finally, the potential biological implications. There's a lot of work that goes on about anti-fouling, antibacterial coatings of graphene. So there's a lot of work that you can read up on in that. And I think, in short, the graphene tends to change the surface chemistry, the hydrophobicity, the surface energy, and it stops the attachment of different biological molecules. I mean, there's a lot more to it than that, but that's just briefly. So the GEIC, the Graphene Engineering Innovation Centre, this picture I like very much because it's what we call the high bay area, and it's where we use pilot scale equipment. We can move things in and out of the building. It's all very fluid, and it's nice because it shows you the scale at which we're working. We're not lab scale. We don't make things on the gram scale. We're going towards production and development of real products. We've been open since 2018, December. It's a £60 million building, and it was built specifically to take graphene from the lab into real applications. Obviously, Manchester's also got the National Graphene Institute, which opened in 2015. Is more research and development and looking at different properties of graphene and how they can be applied in different areas. So the people at the GEIC, the people that are employed, they're a mixture, academics and people from industry. The idea is that we can understand the work that comes out of the universities, that pure research. We can understand it enough to take it and translate it into new products and new technologies. And as I've said, we're very much industry-led. So we work closely with industrial partners to try and understand the problems they have, or to help them create new materials. So in that sense, it's a very different model. We need to do it from both sides. We need industry because they know their product. You know your coating better than we do. we know graphene, you need those two sides to come together. And that's why we can do very quick projects, because we work hand in hand with industry. If something looks like it's not going to work, we'll stop it and we'll do something different. So we're not talking 2, 3, 4-year projects here. We're talking months, fast turnaround. We want to push products to market. This is just some pictures of my coating lab, our coating lab. I won't talk about it too much. I know we're stretched for time, but we have pilot scale equipment. We have a pilot scale coating line. So the idea is that things that come out of here are ready for production. As I said, we're not working on the small lab scale here. There's different ways to engage with the GEIC. We have tiers. These are some of our key strategic tier 1 partners. Graphene suppliers, steel producers, aerospace. Tier 1 partners tend to have their own lab at the GEIC. They bring their own staff in, they have their own people, we all work together. They get to work with our specialists, and they get to use all the equipment that we have in the building. We also have different levels of engagement. So we have tier 2 partners who tend to use shared labs more, maybe not on site as much, but both tier 1 and tier 2 partners tend to run multiple projects at the same time across different application areas. The idea of being a member is you get access to all these different areas. We can also run just projects for people if that's the engagement route you want, and we have affiliate partners as well who may offer complementary services or help to drive projects. Basically, as I've said at the beginning of today, there's not just one kind of graphene. There's many good graphene suppliers that are building up that supply chain. But you can also buy cheaper many layer graphene, which really won't give you the benefits that you're looking for. And basically what I'm saying is it's not just a case of mixing in a wonder material and it'll work. It takes know-how, it takes processing, it takes quality starter materials, understanding exactly what you're dealing with, and methods to determine the dispersion of your graphene within your material. I hope that you've been convinced today that graphene has potential in anti-corrosion coatings, fire retardant coatings. It's got incredible barrier properties. What it tends to do is bring a multifunctional properties to your application. You put it in to do one job and it ends up helping in other ways, and that works across the board. Anyone who works with graphene tends to find this. Compared to some other applications, high-end electronics, medical, that kind of thing, graphene and coatings is probably more straightforward route to market. There's already products out there that you can look up. That's it for today, but I hope you found it informative. And if you have questions or you want to get in touch with me directly or the Graphene at Manchester team, all my details are there.
Thanks very much, Lisa. That was a really good presentation. There is an email address for both Lisa and the Graphene website team as well, so feel free to contact us on there. Any questions to follow up on that? There was a quick one here from Janish. Does graphene coatings change the appearance of the metal?
Change the appearance of the metal?
Yeah.
No, not that we've known. Again, though, we're talking about composite coatings, so probably thicker coatings that are maybe at least 10 nanometers thick. So you wouldn't see an effect there. If it's just graphene, like a single layer of graphene, yes, it will change the appearance of the metal. And you can see that it changes the optical properties of the metal sufficiently, only by a tiny amount, that the metal does look slightly different. Mm-hmm. So in that sense, it probably would. But in this kind of coating, in a paint, no, I don't think you see any difference.
Okay. Quick question from Jason. Do you happen to know how the UV degradation works on the coatings that you tested?
We haven't actually done that testing. We don't have the capability. It's more from research papers. From what I understand, it's all about surface area and absorption capability. So it absorbs the the light preferentially, or the UV part preferentially over the coating system. I think that's how it works, but I could probably get you some more information on that if you want. I found a good couple of papers on it yesterday that I can forward on if that's of any use.
Great. I think we'll leave it there for questions. If you just want to flip to your last slide again, because someone asked about the references slide, so they might take some notes of that. I'm just going to post in the chat now, everyone. So there's a link I've just put in the chat. If you all could, while we're on this call, click on that link. There's a really short survey that would be really good if you could fill in. Give us your email address and let us know what materials you want us to send to you, whether it's the slides, which we're happy to share. We could share the video. We could share a bit more basic information about graphene as well. Or if you want nothing at all, we can just leave you alone. But yeah, please do.
Enough. They don't want to hear any more about it.
I think some might, though. That's the point.
Right.
Yeah, please click that link. I'll post it
nice.
again just because it's moving up a bit. If you could do it now while you're on, that'd be great, everyone. And if there's more we can do to help you or to explore some opportunities around graphene coatings, we're happy to do that.
Absolutely. Any questions you've got, we can address those.
Nick, and I think Lisa, I would like to really put up for all the people. I think we have a good working relationship with GEIC. One of the major advantage, what we really believe this organization of GEIC is all about is there is so many different properties that the end customer requires. There are so many people who say, I make graphene, I do this or this. But the evaluation on the end application, on testing and everything, requires a sizable amount of equipments, investments, and really a period of time. And we really appreciate this type of support and coordinated by the team over in Manchester. It really helps for the end. The customer might not be looking out, give me a product I want to try, and let's see. Nobody has the time, effort, or anything. And I think that's where we really appreciate the support. And thank you very much, guys, for coordinating this presentation.
Thanks, Ishan. Very kind words. I think we'll leave it there. Stay safe. Take care of yourselves. And Lisa, anything to add, Lisa, at the end?
I don't think so. Just again, thanks for listening. I'm aware that was a lot of content there, and it's quite hard to squash it all into an hour. So yeah, if anyone wants to discuss anything, please just get in touch with us directly.
Okay, great.
Fine. And thanks again.
All right. Thanks, Lisa. Thanks, everyone, for joining.
Thank you.
Bye-bye.
Bye.